to the afternoon session. So in this session, we're going to have 14 talks, 2 hours, and 12 spotlights. So the first spotlight, is differentially private testing of identity and closeness of discrete distributions. And Ziteng will give the talk.
Okay. Hello, everyone. Thanks for the introduction. In this talk, I will be focusing on differentially private identity testing. And for the closeness testing part, please come to our poster or read our paper. So I'm Ziteng from Cornell, and this is a joint work with my lab mate Huan Yu and my advisor Jaydev. So we all know there is an amazing amount of data being generated every day. And if we assume that for a specific task, our data comes from a specific underlying distribution, given the data, we want to infer something about that distribution. So, a quintessential problem asked in machine learning and statistics is that, does the distribution satisfy a postulated hypothesis or not? So this problem has been studied a lot, but currently we are facing more challenges. Although the amount of data is increasingly large, the domain size of our data is also large. For example, the data may be over very high dimensions, so we may incur the curse of dimensionality. And additionally, the collecting process of the data may be expensive. So we need to consider the sample complexity of the problem. And on the other side, since the data are collected from users, the samples may contain sensitive information about them. So we want to perform our task while preserving the privacy of each individual. This problem can be modeled as the following identity testing problem. So given a discrete set of size k, and we have a known distribution Q over the set, this is the postulated hypothesis we want to test. And given n independent samples from the underlying distribution, the question we want to ask is whether P equals to Q. Okay, more specifically, we want to come up with an algorithm which satisfies the following, with probably at least 2/3. The algorithm should output 1 if the distributions are equal, and it should output 0 if the distributions are of distance alpha away from each other, and the distance is measured by TV distance. So the sample complexity is defined as the least number of samples where such a tester exists. Without privacy constraints, this is known to be root Q over alpha square, and there are various works obtaining this. And to impose privacy constraints, we use the notion of differential privacy, which is arguably the most popular notion currently. What it requires, roughly speaking, is that if the input data set only changed by 1 data point, then the output probability of any subset in the output domain shouldn't increase by a factor of e to the epsilon. Okay? Before us, there are some works considering this problem. More specifically, Tsai et al. Proposed an algorithm which gives the following upper bound. And in this work, we want to calculate the exact sample complexity of identity testing. And it turns out that the exact sample complexity is the following term. And in addition to the term of the non-private case, and the extra penalty imposed by privacy is the max of these 3 terms. And in each of these 3 regimes, one of the terms will dominate. For example, the first case is a sparse case, where you have samples less than the domain size. And the last case is an extremely dense case, where you have samples enough to learn the distribution up to accuracy alpha. And the second one is the middle case. Okay, and our contribution is that we propose new algorithm achieving the following upper bounds. And we also propose a new methodology to prove lower bounds for hypothesis testing, which gives a tight lower bound for this case. Okay, for our upper bound is obtained by privatizing the statistic used by the Nicholas et al., which is sample optimal in the non-private case. And we want to mention that there is an independent work in this year's ICML, which gives a different upper bound, but their upper bound is only tight in the sparse case. To prove the lower bound, we give the following coupling lemma. It states that if there exists a coupling between the 2 hypotheses that we want to test, and the expected timing distance between the coupling is smaller than d, then any epsilon differentially private hypothesis testing algorithm couldn't achieve a privacy level lower than 1 over d. If epsilon is larger, it means we have stricter privacy constraint. And then to prove the lower bound, we recall Lee Camp's 2-point method, which is very powerful. Hopefully, we can describe in more detail in our poster session. And then we construct two hypotheses and the coupling between them with small expected Hamming distance. Then the lower bound will follow. Our paper is available on arXiv, and see you all at the poster session. Thanks. These are the references.
So the next talk is local differential privacy for evolving data, and Matthew is going to give the talk.
Hi, everybody. I'm Matthew Joseph. I'm a grad student at Penn. And today I'm going to be talking a little bit about local differential privacy for evolving data, which is joint work with my advisor, Aaron, John Altman, and Bill Wagner. So the high-level motivation for this problem is that you have some set of users. These users have some data, and you have an analyst who wants to learn about that data. The sort of tension is that users want to keep their data private. And the question is, how can an analyst learn from this private data? And you can also ask for a little twist is, what if the data is changing or evolving over time? So here, privacy is going to mean local differential privacy, which is a variant of differential privacy where each user randomizes their own data, and the analyst learns on this randomized data. And intuitively, this provides privacy because the randomness sort of obscures any individual data. So for example, suppose you manage a grocery store and you want to know if your customers prefer oranges or pears, and you want to do it while giving them some level of privacy. So you have some N people, each of them has a private opinion over whether oranges or pears are better. And to do this privately, there is a nice known solution called randomized response. And what you do in this case is you give everyone some biased coin P, where the probability of heads is P greater than 1/2. And what you do is have each person flip their coin independently. If it comes up heads, they tell the truth. If it comes up tails, they tell the opposite of the truth. So here, each user is going to flip their biased coin. So the first user, they flip their coin, it comes up heads, so they tell the truth, say they prefer oranges. The second user, the coin comes up heads, so they tell the truth and say pears. But for the third user, their coin flip comes up tails, so they tell the opposite of the truth and they say orange, and so on. And what you as the grocery store manager can do is just add up these responses and take the most common response as your answer. And with high probability, all of this randomness sort of cancels each other out, and your answer is going to be correct. And what happens here is that you learn about the population, but you don't learn about individual users. So you'll learn that like most people prefer oranges, but for any given user, you won't have a good idea of what they individually prefer. And the way this works is users get privacy through the plausible deniability of their random coins. So whatever any given person says, if they say pear, they can always say, oh, that's not what I actually believe. That's just the way the coin flipping randomness worked out. And so the intuition is the higher the bias of this coin, the more accurate this process is going to be, but it's also going to give less privacy to people. If P is like 0.99, people don't really have much room to say, oh, it's just the coin that did that. It's not what I believe. So with this problem in mind, we can consider a twist where the data is changing over time. So for example, maybe in the spring and summer, people prefer pears, but then in the autumn, they start preferring oranges, and then they go back to preferring pears in the winter. And so with this new problem, we can maybe just reuse the old solution and do randomized response every day. But the issue with doing this is that this may reveal private data over time, or the privacy loss will add up. If you think about it, if you are looking at some stream of user responses and you see some sort of bias towards saying orange, that's going to sort of let you infer that probably that person actually prefers orange. So the question that we have is, can the analyst still stay up to date without compromising individual user data? And what our paper says is that the answer to this question is yes. At a high level, our solution relies on users voting on when to update these out-of-date statistics. And this enables the analyst to track distribution changes and guarantee that users only lose privacy when the underlying distribution actually changes. In this setting, we get a worst-case privacy guarantee. Regardless of how the data in question is generated, we can always guarantee local differential privacy for each user. And when we do have a nice structural assumption on the way the data is generated, it comes from some distribution, then we also get a formal accuracy guarantee. For more information, please look at the full archive paper or come talk to me at poster 153 in a couple of hours.
So the next spotlight is differentially private k-means with constant multiplicative error. So Rory is going to give it.
Okay, so hi. This talk is about differentially private k-means clustering. So first, something easy. What is k-means clustering? I'm sure you've all heard about k-means clustering, but I'll show you the definition quickly anyways. So in k-means clustering, we are giving a set of n input points from some metric, let's say the Euclidean space R to the D, and our task is to come up with k-centers that minimize the sum of square distances between each input point to its nearest center. So okay, that's fine, that's k-means, I'm sure you've all heard about it. It has lots of application, we like it. But what is differentially private k-means clustering? So in this model of differentially private k-means clustering, we assume that each of these data points, each blue point here, is the private or sensitive information of one individual. Now we want to achieve exactly the same goal. We want to come up with k-centers with low k-means cost, but we want to do it while also satisfying some notion of privacy for each individual whose data is in this database. And under differential privacy, we say that privacy is preserved if our algorithm is such that for any arbitrary change of one data point, the outcome distribution of centers that it outputs remains roughly the same. So that's differential privacy applied to the context of k-means. And why is that a good privacy definition? Well, because if you have such an algorithm satisfying this requirement, then if you have an observer or an adversary that knows exactly all of the data points except for my point, and then this adversary is looking at the outcome of our algorithm, then still by looking at the outcome of our algorithm, this observer cannot learn basically anything about my data, because from his point of view, no matter what was my data, the outcome that he would have gotten would have remained roughly the same. Okay, so that's differentially private k-means clustering. Nothing happened. I just copied to the top the definition of k-means clustering and the requirement of differential privacy. And now I want to put my finger on an issue that we have right out of the definition of differential privacy in this context. And the issue is the following. Usually when people construct approximation algorithms for the k-means clustering, they consider multiplicative error guarantees. But under this requirement of differential privacy, we're going to have to be okay also with an additive factor of approximation. Why is that? Let's look at this picture here. So the number of points is 3, and k is also 3. So without privacy considerations, it's a trivial input. We just place a center on each of these data points, and the cost is 0. And now what happens if I were to move one of these input points to some faraway side of the input space? So without privacy consideration, nothing changed basically. I will just move the center to that new point, and the optimal cost remains 0. But because of the constraint of differential privacy, the set of centers that we compute essentially cannot be affected by this change. So what we get is that at least on one of these two input instances, we're going to have a large additive error that depends on the distance by which I moved these points. So under differential privacy, we have to have also an additive error, and this additive error depends on the diameter of the input space. So a typical assumption in differentially private k-means clustering is that the input points come from the d-dimensional unit ball, from the d-dimensional unit ball. Okay, so that's my last slide, and what I'm going to show you now is some of the most relevant previous works on differentially private k-means clustering algorithms. And in the bottom in red, that's the new bound. So basically, all of the previous results, they either presented algorithms with exponential runtime, like the first result on the top, or they presented algorithms with super constant multiplicative error guarantees. So in this work, we present a new polynomial time algorithm achieving constant factor multiplicative error while keeping the additive constant factor multiplicative error while keeping the additive error roughly the same as in previous state-of-the-art results. Okay? And that's it. Thank you.
The next spotlight is a spectral view of adversarially robust features.
Hi, I'm Shivam, and I'll describe our work, a spectral view of adversarially robust features. This is joint work with Vatsal Sharan, Brian Zhang, and Greg Valiant. In this work, we try to give a new perspective on the problem of adversarial robustness by using some connections with spectral graph theory. So first of all, what are adversarial examples? In the past few years, it has been observed that most of the state-of-the-art classification systems can be fooled by adding a small amount of noise to the test data. These noisy data points are often known as adversarial examples. Despite the intense research efforts in trying to come up with classifiers that are robust to such noise, we have had limited success, and the problem has turned out to be extremely difficult. Moreover, we don't have a good understanding of many basic questions in this area. For example, what are the trade-offs between the amount of data available, accuracy of the trained model, and vulnerability to adversarial examples? I believe there's going to be another talk in this session that discusses some aspects of this question. Another very basic question is, what properties of the geometry of data set make models trained on it vulnerable to adversarial attacks? This problem was one of the motivations behind our work, and we try to understand it by looking at the simpler objective of finding adversarially robust features. So before I tell you what robust features are, what is a robust classifier? A robust classifier can be thought of as a function from your data points to reals that has two properties. First, it shouldn't change much with small perturbations to data, and it should agree with the true labels as much as possible. Now let's relax these conditions a little bit. I want you to give me a function from data points to reals that doesn't change much with small perturbations to data, but it need not agree with true labels. Such a function can be thought of as a robust feature. And in addition, we require this function to have sufficient variance across the data points to preclude the trivial constant function. So this way of looking at the problem disentangles the challenges of robustness and classification performance. Not only can it help us in understanding some of the basic questions about robustness, it may also be useful in coming up with robust classifiers. So the hope is that if we can come up with many such robust features, training a classifier on top of them will yield a robust classifier. Now, how do you come up with robust features? For this, we spot some connections with spectral graph theory. In spectral graph theory, we associate a special matrix with graphs called the Laplacian matrix, and the second eigenvector of this matrix is the solution to the following minimization problem. In this minimization problem, we are basically trying to assign values to vertices of the graph that change smoothly across neighbors, and the constraints ensure there is sufficient variance among these values. If you think about it for a minute, at least at a superficial level, this sounds very similar to robust features. In the case of robust features, we are trying to assign values to data points that change smoothly around small neighborhoods of these data points. So in our work, we formalize this connection. Given a data set, we create a graph out of it where the vertices correspond to the data points and the edges correspond to some measure of similarity. And we show that robust features can be obtained from the eigenvectors of the Laplacian of this graph. We give an upper bound which characterizes the robustness of these features in terms of the spectral gap and eigenvalues of the Laplacian. We also show a lower bound that roughly says that if there exists a robust feature, the spectral approach would find it under certain conditions on the properties of Laplacian. We also perform some experiments in which we try to test the efficacy of these features for the downstream task of classification and get some promising results. I'll skip this. So to conclude, there are two takeaways I would like you to remember from this talk. The first is viewing the problem of adversarial examples from the point of view of robust features disentangles the two goals of robustness and classification performance, and it can help us increase our understanding of the whole phenomena as well as get robust classifiers. And the second is there are some interesting connections between spectral graph theory and adversarial robustness. If you would like to know more about this work, please come to our poster session, which is at 5 p.m. today in the room adjacent to this. That's it. Thank you.
So our next talk is the oral. The title is Model Agnostic Private Learning, and Rafe and Aberdeep will give the talk.
Last time I checked, it was showing up.
Here you go.
It's showing up?
Yeah, do escape maybe and then.
Yeah, maybe.
Yeah,
Okay. So this is a joint work with Raif Basili from Ohio State, Om Thakkar from Boston University, and Abhadeep Thakurta from UC Santa Cruz. And Om is in the job market. The talk will be shared between Raif and myself. So what is this paper about? This paper is about designing privacy-preserving learning algorithms via black box transformation on any learning algorithm with reasonable accuracy guarantees. Moreover, these transformations will be model agnostic in nature, meaning that you will not depend on the underlying learning model. So there are two main contributions in the paper. The first is a framework for privacy-preserving prediction. But the idea is, suppose you are given a sensitive training data set. This data set may have information like some haptic feedback from your phone and a bit telling whether you have Parkinson's disease or not. And there is this framework, the privacy-preserving predictor, APRIV, whose objective is very simple. What it should do is, given a feature vector, it should provide the label or classify those feature vectors. Not only it should do for one of them, it should do for many of those such feature vectors. And the requirement from privacy perspective is that this algorithm APRIV should not leak too much of sensitive information about the training data set. Since we are looking at black box construction, the algorithm only has input-output access to the non-private learner. Okay. The second main contribution of the paper is to extend this idea to actually train or release a classifier which can later predict on any number of examples or feature vectors. So the idea is to use the same framework, but now think that these feature vectors on which you are predicting come from some public data set. This you can think in the language of mobile companies, opt-in users, where you have the feature vectors, but not necessarily the label, meaning that the bit for Parkinson's disease. What you do is you get the labels for these feature vectors via the framework, and then you feed it to any non-private learner of your choice. In particular, you can use the original non-private learner, and that would give you the trained classifier. Okay? Now, since this trained classifier only accesses the sensitive data to the, through the algorithm APRIV, it does not leak any more privacy beyond what is leaked by APRIV. So just to recap the design requirements for our system, we need, first of all, the algorithm needs to be black box, access to the non-private learner. Number two, it should be able to handle a large number of queries. Number three, it should have rigorous privacy and accuracy guarantees. Moreover, since we are looking at black box construction, it is only good to hope that the accuracy guarantee of the non-private learner should seamlessly translate to the accuracy guarantee of the private learner. Okay? So till now, I've been telling you that we will protect privacy. What privacy we are really protecting? Well, this is not surprising. We are following the notion of differential privacy. So here I will not go through the definition because speakers before me have introduced the notion, But what differential privacy essentially tells you is that given the output of an algorithm, the adversary should not be able to distinguish the presence or absence of a particular user in the dataset. In particular, a particular person with Parkinson's disease or not should not be distinguished by the adversary from the output of the algorithm. There are two parameters you need to remember from this slide: the parameter epsilon, which is typically a small constant, and the parameter delta, which is roughly 1 over the size of the dataset squared. Now, coming to prior work, there has been a series of work on similar ideas. Because of time constraint, I cannot go over all of them, but I should mention 4 key features. First, either the prior work was looking at non-model agnostic algorithms, or it was dealing with white box construction where you actually open the algorithm and make modifications to make it private, or it was looking at single query setting, or it did not have formal accuracy guarantees. So our paper actually scores on all 4 cases. So just to give a high-level idea of the kind of results we have, well, we designed black box algorithms with non-private learners. Our algorithm is differentially private. Furthermore, as compared to the prior work, it can answer at least 1 over alpha more queries than the prior work, where alpha is the misclassification rate of the non-private learner, which basically means if you have a very strong non-private learner, then you can boost up the number of queries you can answer for the same privacy and accuracy goes up significantly higher as compared to the prior work. Well, since we are looking at formal accuracy guarantee, even for the classification or the classifier, what we show is that our sample complexity bound for the private classifier is comparable to the sample complexity bound for the non-private classifier. And from here on, Raif will take you through the rest of the talk.
All right, so in the remainder of the talk, I will give a quick synopsis about our constructions and technical results. And let's start with our private algorithm for classification queries. So this algorithm combines 2 techniques from the literature of differential privacy, namely the sample and aggregate technique and the sparse vector technique. The first step in this algorithm is to partition the private training set into k-disjoint parts of equal size, and then use each part to train your favorite non-private learning algorithm. And hence, we end up with an ensemble of k-classifiers. Now, as you would expect, for every queried feature vector, we obtain the votes of those classifiers on this feature vector, and then compute the margin between the count of 1 votes and the count of 0 votes. Now, when this margin is large, this means that the majority vote is going to be stable with respect to small changes in the input training set. So following the definition of differential privacy, intuitively, we would expect it to be safe to output the majority vote when this margin is large enough. However, we cannot just make such a decision based directly on the actual value of the margin, because this is actually a deterministic function of the private data set. Instead, we test for stability in a differentially private manner. So we add some amount of noise to this margin, and then we test whether the noisy margin is large enough. If the answer is yes, which means that this prediction or this query is stable, then we safely output the majority vote. But if no, we output a random label. Now, from the properties of the noise, we can show that if this margin is sufficiently large, the actual value of the margin is sufficiently large, then with high probability, the output of the algorithm for that query is going to be the majority vote. Now, this procedure is repeated for every input query, every input feature vector. However, to ensure epsilon delta differential privacy for the entire sequence of input queries, our algorithm has to stop after roughly about k squared, epsilon squared unstable queries or unstable predictions. So one important aspect about this construction is that the privacy budget is consumed only by unstable queries or the unstable predictions. No privacy cost is incurred for the stable queries, and that's what mainly allows us to answer more queries than prior approaches. Now, for this construction, we can formally transform the accuracy guarantees of the underlying non-private learner into accuracy guarantees for our private predictions. In particular, suppose that the non-private learner has a misclassification rate, which is bounded by some fraction alpha. Then we can show that for a sequence of m queries, our algorithm cannot make more than 3 m alpha classification errors. And to prove this result, to actually use a simple counting argument to show that for every query, except for at most 3 m alpha queries, a significant majority of the classifiers will agree and will agree on the correct label. So we have stability and we have correctness. One implication of this result is that, as we mentioned before, our algorithm can answer at least a factor of 1 over alpha more queries than prior approaches that was directly based on a direct application of the so-called composition theorem of differential privacy. Now, our next task is that we're going to use these private predictions we have generated on public feature vectors to form a new training set, or a proxy training set, if you may. And we're going to use this new training set to train any good non-private learner and finally output a classifier. And this classifier would be safe to publish and can be used to answer unlimited number of classification queries. Due to time limits, I will not have time to go through the technical details of this part, but the main idea is that we can formally analyze the accuracy of the final classifier by combining these two facts. Fact number 1 is that by the accuracy guarantees we have just shown for our previous algorithm, we can argue that the misclassification rate in this new training set that has the private predictions is going to be small. And the fact number 2 is that if the non-private learner is a good learner, then we expect the final output classifier to have a misclassification rate that is close to the misclassification rate within this new training set. Using these ideas, we finally derive a private sample complexity bounds in the PAC model, and our bounds are compatible to the optimal non-private sample complexity bounds for both realizable and agnostic cases. In particular, our bounds are worse by only a factor of about square root of the VC dimension of the target class divided by square root of the error parameter. And just to sum up this work, we give a new algorithm for differentially private predictions, and then we give a construction that transforms those predictions into final private classifiers, assuming we have access to some public unlabeled data. And our constructions only require black box access to a non-private learner, and they are equipped with formal accuracy guarantees. And I'll stop here with the poster information, and our poster is located downstairs. Thank you.
So we have time for a few questions. If you have questions, please go to the microphones. So I'll ask the first question. So it's a very nice talk. And do you think it's possible to generalize your work from classification to regression?
That's a great question. Actually, that's a great question. So there are definitely some challenges with the regression case. The main challenge is basically the algorithm worked for a discretized range. So we need to do some sort of data-independent kind of discretization in the regression case. So without further assumptions on the data distribution, we may have some guarantees, but not as strong as a classification case. We do have in the archived version of the paper some results for the soft label classification case. But generally speaking, for regression, it's more delicate to deal with. But if the final guarantee if the task is a classification task, even if we use a surrogate loss model, it doesn't have to be the 0-1 or the back model, we still have similar guarantees.
Any other questions?
So it seems like in your method, you need to have access to some public non-private data. And this is also like a property of earlier algorithms. But this like black box style transformation, is like that essential, or is there some hope to have algorithms that work without public data?
Yeah, so for training the classifier, you do need access to the public data. Yeah. So
And can this be avoided, or is it like essential?
If I may add something, it has been shown there are lower bounds in differential privacy that if you don't have that, you will have some sort of explicit dependence on some nasty parameters, like, for example, the size of the hypothesis class, model class.
The size.
Sometimes, yeah. Even for simple tasks like learning thresholds. So, or on the dimensionality of the parameter space sometimes. So to avoid that, we make this assumption.
Cool. Awesome. Thank you.
Let's send to the speaker. So our next talk, Spotlight, is bounded loss private prediction markets. Bo will give the talk.
All right, great. Hello, everybody. So this talk, again, is on bounded loss private prediction markets. It's joint work with Ralph Frangillo at Colorado. OK, so let me tell you what a prediction market is, at least from a sort of machine learning perspective. So we have a platform or some sort of learning or aggregation algorithm, and the goal is to maintain predictions about some future event. So political or sporting event or the weather, whatever. OK, and to do that, it's going to collect information from participants. Okay, so when a participant arrives, the algorithm is going to offer it a menu of purchases that it can make, and these purchases essentially translate to gambling on the future event. Okay, so the participant is going to choose one that it thinks is best, and the algorithm is going to learn from that information. So it'll incorporate that choice into an updated prediction. Okay, so we keep repeating as participants arrive, and there's a lot of theory about how you should do this and how that algorithm should work. But not crucial to this talk to get into the details. Okay, after everyone arrives, the final event will be observed, and then based on that event, the algorithm has to pay off to the participants based on what they purchased, what their gambles were. Right? And in particular, it's known in classical prediction markets how to do this with any bound you want on how much money you're going to spend as this algorithm. Right? So you can say beforehand, I want to spend up to so many dollars, and you can guarantee that no matter what the participants do, you'll spend no more than that, and no matter what the event is. Okay, good. So now let me talk about differentially private prediction markets, which is the subject of this paper. So 3 years ago, in this building, actually, with Jake Abernethy, we had a paper on differentially private prediction markets, and also some machine learning connections that I'll touch on at the end. You've seen differential privacy, so I'm not going to go into the definition, but they preserve the privacy of these choices that the participants are making at each time. Okay, the main drawback was that the financial loss of the mechanism may not be bounded in the number of participants. So the more people who arrive, the more money you might have to spend, and there's sort of no way beforehand to cap that while still preserving privacy. Okay, and this is not a coincidence. So there's a paper that was essentially concurrent that showed an impossibility result, and it said that all private prediction markets that use a certain framework, which we also used in this previous paper, are going to suffer from this problem. Okay, and the reason is really simple, actually, or the reasoning, the proof is not, but the reasoning is just that you add some noise to preserve privacy, right? And then that introduces errors in your prediction. The next person can come in and expect to make money off of you by correcting those errors. But then you need to add some noise to preserve that person's privacy, and so that introduces more errors. Okay, so what do we do in this paper? In short, we sort of sidestep this impossibility by going a little bit outside this standard framework, which I can tell you about when you come to the poster. And we end up with something that we like a lot because it seems to satisfy all the properties we want for any mechanism that's gathering information and making predictions about a future event. So differential privacy for the participants, the information they're providing or the choices they make. The incentive to participate means that if the predictions of the current algorithm are wrong in some way, if they're off by some amount, then there's an opportunity to make money by correcting those predictions. By accuracy or fidelity here, I just mean that the noise you add to preserve privacy doesn't distort your predictions too much. And then finally, the aspect that we incorporate in this paper, you can set a bound on how much you're willing to spend beforehand and guarantee that no matter how many participants arrive, you'll satisfy that bound in expectation over your own randomness, but worst case over what the participants do and what the event turns out to be. Okay, and the only thing I'll say about the technique is the intuition is similar to a doubling trick of online learning. Okay, so let me briefly mention some extensions that were in this prior paper that worked really nicely with this result as well. So if you think about that future event that I mentioned that we're trying to predict, imagine that instead of it being some actual event in the world, it's a test data set that's hidden, maybe held by a third party. And the algorithm is maintaining, let's say, a model at each time step. And then at the end, the model is going to make predictions on this test data set, and it'll be revealed how well it does. Then this exact same prediction market framework starts looking like two possibilities, either a sort of machine learning contest that's collaborative, or still like something that's purchasing data or information from the crowd in order to perform well on a machine learning task. And if you're doing either of those things, it's really nice to have all four of these properties. Okay, so for more, please read the paper or come see me at the poster. Thank you.
So the next talk is CPSGD, Communication Efficient and Differentially Private Distributed SGD. Felix will give the talk.
Hey everyone, my name is Felix Yu, and this is a joint work with Naman Aggarwal, Ananda Suresh, Sanjeev Kumar, and Brandon McMahon. So here we consider the setting of distributed learning on mobile devices, where the goal is to train a centralized model, and the data stays on the mobile phones. And in this learning setting, typically in each iteration, the server will first send the model to the client. Here I use this W, a d-dimensional vector, to represent the model. And then on each client, it will compute the update or the gradient of the model with its local data, and then send the gradient back to the server, where the server computes the averaging of the gradient and apply the updates to the global model. So there are a couple of challenges in this learning setting. The first challenge is that uplink communication is often very expensive. One solution of this challenge is to apply quantization on the gradient before sending it back to the server. Here I use Q to represent the quantization operator. Since the convergence of SGD depends on the mean squared error of the estimated gradient, in order to understand how to design the best quantization algorithm, it is sufficient to study the bits versus quantization error trade-off simply in the distributed mean estimation setting. For example, if you do not do any quantization and assuming float, then we need 32 bits per coordinate, leading to zero mean squared error. And a simple binary quantization will give you 1 bit per coordinate and mean square error on the order of d over n. And during the past 2 years, there have been multiple papers improving the results. The second challenge here is that user privacy is very important. Here we use the notion of differential privacy, which states that removing or changing single client's data should not result in big difference in the estimated mean. In the distributed learning setting, differential privacy is often achieved by adding Gaussian noise. And the goal of this paper is to propose an algorithm which can address both of the challenges, achieving communication efficiency and differential privacy. This turns out to be a tricky problem. Our first attempt is to add Gaussian noise simply on the server. The good news is that differential privacy results are readily available if we assume that the L2 norm of the gradient is bounded. However, in order for this to work, the client has to trust the server to add the appropriate noise, which may not always be the case. Our second attempt is to add the Gaussian noise on the client. For example, you can add the Gaussian noise after quantization, and this is obviously not a good idea because Gaussian is continuous and you won't have communication efficiency. Or you can add the Gaussian noise before quantization, and it turns out this is very hard to analyze because we need to understand the distribution of sum of quantized Gaussians, which is the multinomial Poisson distribution. In this paper, we proposed the CPSGD algorithm, which adds binomial noise after quantization. So CP-SGD maintains the communication efficiency because the binomial distribution is discrete. The proposed algorithm is differentially private in the sense that binomial behaves very similarly to Gaussian. And in the paper, we have extended the existing results to d-dimensional data with improved bounds. This works if the server is negligent but not malicious in the sense that the server simply computes the average of the gradient. And this works even if the clients do not trust the server with the secure aggregation algorithm. So our main result in this paper states that for D variables and N clients, where N is close to D, the proposed algorithm achieves log ND bits of communication per client per coordinate with constant privacy. And we have verified the result with experiment. If you would like to know more, please come to our poster downstairs. The number is 27. Thank you.
So the next talk is adversarially robust generalization requires more data. Ludwig will give the talk.
Cool, okay, thank you for the introduction. So I'm going to talk about joint work with Shribani Santurkar, Dimitris Tsipras, Alexander Madri, who are all at MIT, and Kunal Talwar, who's a Google brain. So this talk is about adversarial robustness. So I think everyone in the room is by now familiar with the concept of an adversarial example. This phenomenon has received a lot of attention over the past 5 years in the machine learning community. Yesterday there was a great tutorial by Siko and Alexander. And in spite of all the sort of research devoted to this problem over the past 5 years, we are still quite far away where we would like to be. So on standard data sets like CIFAR10 and ImageNet, these networks, even when we use all the tricks we have, are still quite vulnerable to adversarial examples. So one natural question is why? Why do adversarial examples turn out to be such a hard problem? And sort of in this talk and in this paper, we want to give one perspective on this question based on sample complexity, basically from the theory side of generalization. Okay, so before I go into our result, let's first briefly recap sort of what we want to contrast in this work. So here, this is the standard definition of the population risk. I think everyone has seen this before. This is how we normally evaluate the quality of a classifier in machine learning. So basically, we take the average over data points from our distribution and then compute the loss of our classifier F on the data points from the distribution. And sort of this is great, it gives you a good average case guarantee, but it's important to realize that this definition is entirely compatible with your classifier being very vulnerable to adversarial examples. So even if your standard risk is very low, it can still be very vulnerable to adversarial examples. And so because when we talk about adversarial robustness, what we're really talking about is this type of definition. So we still have an expectation, we have an average over points from our distribution D, but now before feeding the data point X into our classifier F, we first let the adversary act on the data points. In particular, there are some perturbations at P, could be small L infinity perturbations, rotation, translations, and so on. And after the adversary's action, we measure the loss of the classifier F on the perturbed data point X prime. Okay? So this is a different way of measuring the quality of a classifier. And now an important question is, how do these two notions compare? Maybe the second one is just harder to achieve. Okay, so you might ask now, okay, is this sort of in any way related to the state of the art and robust classification? And the answer is yes. Actually, this very well characterizes what we see in practice. So this is the current state of the art in L infinity robustness. The paper Alexander's group and I wrote last year on how to do a robust optimization for L infinity robustness. And on MNIST, so one of the two data sets we looked at, we see that things work out very nicely. So in this plot, we have x-axis number of training steps, y-axis accuracy, and throughout training, the adversarial train and test accuracy nicely track each other. This is exactly what you want to have if you want to have a model that generalizes well. And at the end of training, we do get good adversarial accuracy, about 90%, against a fairly strong adversary on this data set. But then, when we go to CIFAR10, things suddenly look quite different. So in particular, we still get 100% adversarial robustness on the training set. Sort of the blue line here still goes to 100%, which tells us that optimization does succeed. So we do end up with a model that is robust on the training set, but unfortunately, this robustness does not transfer to the test set. So the orange line, which tells us that test accuracy still sticks around below 50%. So we have about 50% generalization gap here. So this was surprising to us because it tells us there's really some amount of overfitting going on. And then we were asking, okay, maybe this is something we should expect. So if we hold the data set fixed? Should we expect a larger amount of overfitting when it comes to the adversarial risk? In order to understand this better, we looked at a simple theoretical model, so a simple natural data distribution, and asked the question, does robust generalization in this model require provably more data? And so if the answer is yes, so I don't have time to go into much details, but already in a natural simple distribution over points in RD, we see that learning an L-infinity robust classifier provably requires more samples. So the gap is square root D times the sample complexity of standard generalization. So if you're in a higher dimensional problem, like image, let's say, you do also see a larger increase in sample complexity. So since we are running out of time, let's conclude for now. Now one question you might ask, okay, what about MNIST? We saw that things are easy on MNIST, and indeed we do have a second data model in the paper that sheds some light on why MNIST is a particularly easy case for L-infinity robustness. And we have more experiments on a variety of data sets to understand what's going on empirically. So I think the main takeaways are that sort of, or in a simple natural distributional setting, sample complexity can be a provable obstacle for adversarial robustness. This has various implications for practice. I think one important direction to look into is how can we improve the priors that we encode in our models. And I think there are many questions left on the theoretical side. I'd be happy to chat more at poster number 31, and I recommend you check out our blog at gradientscience.org. Thank you.
So the next talk is attacks meet interpretability, attribute steer detection of adversarial samples. Now Guanhong will give the talk.
Good afternoon. I'm Guanhong from Purdue University. I'm going to present our paper, Attacks Meet Interpretability, Attribute Steered Detection of Adversarial Samples. As the previous presenter noted, the adversarial samples are just a small perturbation added to the benign inputs will lead the model to wrong predictions. So let's look at how this kind of situation would happen if we ask a human to recognize these two almost identical images. They may focus on high-level features such as eyes, nose, and mouth, and give us the correct answer. Based on this observation, we have the idea that the classification of a model should be based on human perceptual attributes. Thus, we propose our architecture called the MI. Given a benign input, we use existing tool to generate facial landmarks, and we ask a human to annotate the high-level features which these facial landmarks belong to, and then we try to extract attribute weaknesses from the model. That is the neurons correspondent to the attributes. And then we can modify the models based on these attribute weaknesses using their activation values and for each execution. And we can compare their result feed it into the original model and the attribute steered model and to see whether their output is consistent. If not, then the input may be problematic. The hardest part is that how to extract attribute weaknesses. Are there any correspondence between the attributes and the neurons? If yes, then how to extract this kind of neurons? We propose bidirectional reasoning. That is, for the forward reasoning, we change the attributes and to observe whether the neuron activations change. For the backward reasoning, we can change the neuron activations and to observe whether attributes change. However, this is very hard to achieve in practice. Thus, we resorted to use another logical equivalent reasoning procedure. That is, if the attribute does not change and the neuron activation should also not change. Here is the attribute weakness extraction procedure. Given an input, we replace the attribute for this input with the attribute from other inputs, and then we observe the activation value change between these two. And then we can extract the feature variance. This is for the forward reasoning. For the backward reasoning, we can replace the base attribute with other onto other images in the dataset and observe the difference between these two inputs in the model and extract a feature invariance. And then we can intersect these two sets of features and extract the attribute weaknesses. For the experimental results, and we have less than 20 neurons extracted as attribute weakness, even though there are 62 to thousands of neurons in each layer. And for the versatile detection, we achieve 94% detection accuracy for 7 attacks, and state-of-the-art technique can only achieve 55% accuracy on face recognition systems. Thank you. Please come and visit our post at number 99. Thank you.
Next talk is an oral. The title is Learning to Solve SMT Formulas. And Pavel will give the talk.
Okay. Hi, everyone. Thank you for the introduction. My name is Pavel, and this is a joint work with Mislav and Martin, and what we try to investigate is how to learn to solve SMT formulas. And to start, let me give you a bit of background. What is an SMT formula, and what better way than with an example? So what I show here is an example of SMT formula. So this is a first-order logic formula. In this case, it contains 3 variables, b, which is a Boolean variable, and x and y, which are real-valued variables, and a set of constraints that constrain the values of these variables using nonlinear constraints, trigonometric functions, logarithm expressions. And in fact, you can be even more expressive because the SMT defines a set of theories that you can use that additionally include integers, arrays, bit vectors, or strings. And at this point, I would just like to know that for those of you who are familiar with set formulas, the SMT is in fact generalization over set formulas that are defined only over Booleans. Now, given such a formula, the interesting questions that we might want to ask is, does there exist a valid assignment to the variables such that the formula is true? And to answer this question, this is exactly what SMT solvers are designed to do. So the SMT solver takes as an input first-order logic formula and gives as an output whether the formula is satisfiable or not. And moreover, it also gives us a model, which for many applications, this is what we really care about. So if you have a planning or scheduling problem, the model really is the solution you want. Now, SMT solvers are not new. People have been developing and improving them for a lot of years, and they have a wide range of applications. So the most notable one is for software and hardware verification, where the goal is to prove that your program is correct. And this program can be quite complex, such as a compiler or even operating systems. But it has other applications in program analysis, program synthesis, as well as in this community for neural network verification. Now, one of the challenging parts of creating these solvers is that the problem of solving these formulas is really, really hard. And just to illustrate how hard it is, if you want to solve formulas that contain only Boolean variables, this is already NP-complete. If we consider linear real arithmetic, this is doubly exponential. For linear integer arithmetic, it's actually triple exponential. And if we consider nonlinear arithmetic, this is undecidable in general. So one of the challenges to make this fast in practice, what the developers do is that they resort to a set of handcrafted heuristics that are called strategies in this case. And these are defined for a set of common benchmarks and set of common problems. And as a result, one of the disadvantages is that if your problem does not fit into these benchmarks, it's likely that it's going to be very slow. And moreover, what's even worse is that if this happens, you as a user have no way to influence this, because to design these heuristics and strategies, you need expert knowledge in how the SMT solver is implemented, which as a user you just don't have. And this is a problem that we try to solve in our work. So in our work, we try to learn strategies or these heuristics that are fast at solving the formulas. And more importantly, we try to solve it without any prior knowledge about what are the formulas or what are the existing heuristics written by hand. We implemented this in a system called FastSMT, and what I will do in the rest of this talk is give you an overview of how we can achieve this. And to start, let me give you just a bit of additional background about how an SMT solver solves a formula. So at the high level, to solve a formula, we start with the original formula, and we apply a sequence of transformations that try to rewrite or partially solve the formula until we reduce it to either true or false, which are trivially either satisfiable or not satisfiable. And these transformations can be, for example, constant folding, where based on the theory of integers, we know that adding 0 doesn't have any effect. It can be something that tries to rewrite the formula into semantically equivalent formula, but one that is sort of easier to solve later on. It can really change the representation over which we are working. So for example, instead of representing numbers as integers, we can change the representation to be a bit vector representation, where for each bit we introduce a new variable. Or finally, we can use a set of decision procedures that try to solve particular theory. Now, even though I gave you intuition about what are these transformations, in our work, we actually treat them as a black box. And what is only important is to think of them as an action space that the learning will consider. And naturally, the challenging part is that at each point, there is not one transformation that can be applied, but a lot of them. And depending on which choice you make, you can either solve the formula very quickly, or you might not even solve it at all. So with this in mind, how can we go about learning to solve the formula? So the input is a formula and the sequence of transformations that we want to, that solves the formula. And to learn this, one idea might be, well, let's try to learn a model that, given the formula, predicts the sequence. And we can try to do this, but the problem is that this is very hard to learn. And it's very hard to learn because we have no prior knowledge about what strategies are good. And since these strategies can be quite long, any mistake we make along the way is actually going to be very costly for us. So what we would like to do is try to simplify this problem. And one way how we can do it in an elegant way is to phrase this as a reinforcement learning problem. So if you look back at this slide, what we can do is we can just replace the formulas with states, the transitions with actions, and the time it takes to solve the formula we can just consider as a reward. And the problem now becomes to learn a policy that has sort of lowest runtime by exploring this search problem. So how it would look in the practice, so we would take the formula, we would use the policy to predict the next transformation to apply. We would then take this transformation, give it to the SMT solver, which gives us the transform formula, and we do this until we solve the formula. Now, the good thing is that this is much easier to learn because we have all these intermediate formulas that we can condition on. But unfortunately, because we have all these intermediate formulas, the SMT solver actually loses the internal state that it uses for solve the formula. And to give you an example why this is important, if we do, for example, bit blasting, that is change the representation, the SMT solver needs to remember that it changed this x equals to 5 to these 4 different variables. And if it doesn't remember, it means that we are also not able to give back the model. And also one of the disadvantages of this approach is that the policy is actually expensive to run. So if our goal is to have something that is faster than the original heuristics, this might not be the best choice. However, we can build on top of this. So what we really do is to do this as a first step. So first we learn a policy that predicts the next tactic to apply with all the disadvantages that I just described. But to address the disadvantages, there is a second step that tries to extract the policy. So we try to extract an interpretable program that contains branches or even loops that describes the decisions that the policy learned. And with such a program, we can go and replace the handcrafted heuristics that the SMT solvers use with our learn strategy. And this involves no runtime overhead, as well as nice integration with the solvers. So how does these 2 steps work? So for learning the policy, you can imagine there are many ways how we can do it. What worked best in our case is this following neural network policy. It has 3 inputs. So the first one is an embedding of the actions you've taken so far. The second one is a set of formula measures that gives you statistics about the current formula, such as number of constants it has or whether it belongs to a particular theory. And the third one is the representation of the formula itself. And here we try different ways, including bag of words, pre-trained skip-grams, or by looking at the abstract syntax tree of the formula. Using these inputs, we can run it through the network, and we get two types of output. So the first one is a probability distribution over the next tactics to apply, and also a regression over the parameters. So I didn't mention the parameters so far, but you can think of parameters as something that affects how exactly the transformation is going to be applied. To train this, we start with a data set of formulas that we would like to solve, and we first take a formula from this data set and sample the policy. So since we start with no prior knowledge, this policy is at the beginning going to be completely random, but even then it's going to sample some of the traces in the search space from which we can build a training data set, and we can use it to retrain the policy, where in the retraining, we take the loss is the weighted average of the cross entropy and a mean square error for the parameters. And with such retrained policy, we can evaluate it back on our data set of formulas and continue until we are satisfied with what we trained. So the result of the training is a policy, and we can run it on a set of formulas, and it gives us the sequence of actions that are good at solving the formula, and we can do it on a lot of these formulas. And the goal of the policy extraction is now to combine these into a single strategy that can be used to solve all the formulas, not each of them individually. And to do this at a high level, what we need to do is to synthesize at each point where there are multiple outgoing edges in this combined strategy, synthesize a predicate that selects which of the actions should be taken. So in this case, to select whether we should take A4 or A2. Okay, so how well does this work in practice? So to evaluate our approach, we compared against the state-of-the-art SMT solver called Z3, which is developed by Microsoft Research, on a set of benchmarks that are coming from both academia and industry. And for each of these benchmarks, we performed this two-step learning process. First, we learn the policy, and then we extracted the policy into this interpretable program that we use to instantiate the Z3 solver. And what we are interested in is our speedup. So what I show here is a log scale of the speedup over the Z3 solver, where at 1 is the performance of the hand-grafted strategies. Everything above means that we are faster. Everything below means that we are slower. So if you look at the first benchmark, there are two important things to notice. First of all, for all of the formulas, we managed to be faster. And for more than half of them, actually, the speedup is 10x or more. With the next benchmark, we are even better. So we get 2 orders or even 3 orders of magnitude speedup. And of course, there are also benchmarks where the default strategy is already quite good in the Z3 solver. But even in these cases, we actually managed to improve over the hand-grafted strategy. And one thing to notice is that really we start without any prior knowledge. So we don't start at the line that says 1. We start at the line that says 0. And there are also cases when we are slower. And we investigated this, and it turns out they're mostly because the policy extraction is not expressive as the policy itself. So with this, I just want to say that all our code, experiments, our data are available online at fastsmt.ethz.ch. And with this, I'm happy to take questions.
We have time for a few questions.
So I have a question. So you said SMT is NP hard or even undecidable, right? Yes. So your algorithm, does it have any guarantee that it can solve at least part of the formulas?
No.
Okay.
But this is also, I mean, for those that are decidable, we have the same guarantees as the solver itself, right? So if it's undecidable, we cannot give any guarantees. If it's decidable, in the worst case, the guarantees is the same as the solver itself.
So the best we can do is experience, by empirical evidence that this algorithm is good, is fast.
Exactly.
Okay.
I mean, even if many of these theories are solvable, the complexity, if it's triple exponential, if you really have bad luck, this is something that is not going to help you in practice. In practice, you need these heuristics to really make it in terms of seconds, not in 2 weeks.
Okay.
So this is what we try to solve.
But we don't understand the heuristics, right?
Say again?
You said we have some heuristics.
Yes.
But do we understand like why that this heuristic is better?
Yes, I mean the developers of the SMT solvers, of course, they have domain knowledge and they are the ones who develop these heuristics and they are not random. But the way how we exactly combine the heuristics, it's kind of a black magic in black art, right? And for this you need a lot of domain knowledge.
Okay, thank you.
Okay, one more question.
Thank you for your talk. Did you try with only solvable formulas, satisfiable formulas?
Well, we didn't filter the formulas in any way. So we took the existing benchmarks, which contain both formulas that are solvable and both formulas that just time out with any reasonable timeout we could try.
Did you try to learn as a, say, a preliminary task something about the classifying the difficulty of the formula, how much time it would need to solve it?
Yes. So in fact, if you look at the strategies that we synthesize, this is sort of part of the program that we synthesize, because depending on the difficulty, you might want to use different strategies. So internally, it learns some sort of difficulty.
And if I may again, did you ask the experts whether this, say, hierarchy of difficulty was the same as for themselves?
Not really, but we are communicating with the developers of the Z3. We send them our work, so maybe they can give us more feedback.
Okay, so let's thank the speaker. So our next talk is towards robust detection of adversarial examples, and Tian Yu will give the talk.
Hey everyone, I'm Tian Peng from Tsinghua University, and today my topic is about towards robust detection of adversarial examples. Adversarial examples are quite common on deep learning models. As shown in the figure, the left column is normal examples. After adding human imperceptible perturbation, the adversarial examples in the right column can mislead deep learning models. So in this paper, we propose a method to detect adversarial examples. Most of the work on detection of adversarial examples is to design new detectors, for example, the kernel density detector or the LID detector. And but instead, we propose a new training method to make the models better to collaborate with existing detectors. So we first propose a new loss function named the reverse cross-entropy loss. The definitions of cross-entropy and reverse cross-entropy are very similar. The only difference is that in cross-entropy, we use the one-hot label to do the dot product. And in the reverse cross-entropy, we use the reverse label vector, which assigns 0 to the true label and assigns 1 over L minus 1 to other labels. For example, as shown in the right panel, where there are 10 classes, other labels are assigned as 1 nice. And the RCE training procedure based on the RCE loss is also very simple. We first do reverse training to train the model by minimizing the RCE loss. Then we negate the losses fed to the softmax layer to give final predictions. We also have theoretical guarantees on the RCE training procedure. Here we show two important theoretical properties of RCE training. The first property is that RCE training is consistent and unbiased, which means when the training error tends to 0, the prediction will also tend to one-hot label vector. The second property is that the difference between any two non-maximal elements decreases faster than CE training. And these properties makes the feature learned by RCE distributes on low-dimensional manifolds. Therefore, existing detector metric like kernel density and LID and so on will collaborate better with the networks trained by RCE. And here are AOC scores for the detection on adversarial examples. our method largely outperforms the baseline. And for more experiment results and analysis, please come to our poster number 11 downstairs. And our code is also available on GitHub. Thank you.
The next talk is neuroarchitecture search with Bayesian optimization and optimal transport.
All right, thanks for being here, everyone. I'm Kittivasan, and this is work with Willie, Jeff, Barnabas, and Eric, and all of us at Carnegie Mellon. Up until a few years ago, when it came to neural networks, we were mostly using feed-forward networks. But in the last few years, there's been a bunch of innovations around neural networks, such as branching, skip connections, and whatnot. And today, we are interested in automatically finding the optimal architecture for a given prediction problem. Architecture search is a model selection problem in that you want to find the best model, that is the architecture, with the highest validation accuracy. So you can think of it as trying to optimize this function f, which takes an architecture as an input, spits out the validation accuracy as the output, and whose evaluation requires training and validating this architecture on a given data set, which can be quite expensive. And some of you might know that Bayesian optimization methods are well suited for exactly these kinds of problems, that is, these expensive black box optimization problems. And what we want to do in this work is develop a Bayesian optimization framework for neural architecture search. Prior work on architecture search is mostly based off reinforcement learning or evolutionary algorithms, and these methods, unlike Bayesian optimization, are not particularly well suited for expensive function evaluations. So how does Bayesian optimization work? So let's say, for example, this is a function you want to optimize. At a given time step, you're going to use your past evaluations to construct the posterior Gaussian process. And then you're going to use this posterior to define what is called an acquisition function, that is the dotted blue line here. And then the maximum of this acquisition is going to be your next point for evaluation. So now this cartoon looks nice in Euclidean spaces, but now we need to be able to do this in the space of neural network architectures. And what we do in this work is we first define a kernel between neural network architectures, and this in turn allows us to define the GP and compute this posterior. And secondly, we develop a method to optimize the acquisition in the space of neural network architectures. Our first contribution is that we develop this distance called Ottman, which is based off optimal transport for neural network architectures. And given a distance d like this, we can use e to the minus beta d as the kernel. So how would you compute this distance, let us say, between these two networks? What we're going to do is we're going to pretend that there's a pile of sand next to each of these layers. So for example, this layer over here has 32 filters, so it has a big pile. This layer over here has 32 filters, so it has a big pile of sand. But this layer has just 16 filters, so it has a small pile of sand. And what we're going to do is we're going to try and match the piles of sand over here to the piles of sand over here. So I could, for example, take this big pile of sand and match it directly to this big pile of sand. Or I could break it into small parts and match it to these different layers. But we're going to do this in a way so as to minimize a certain penalty function, which is going to account for two things. First, the type of operation. So for example, if I take this pile of sand next to a conv3 layer and match it to another conv3 layer, then that term is going to be 0. But if I take this layer, take the conv3 layer and match it to a conv5 layer, then there's going to be a small penalty. Whereas if I take a conv3 layer and match it to a pooling layer, then there's going to be a very large penalty. Secondly, it's also going to account for structural position. So if I take a layer over here and match it to a layer over here, then there's going to be a small penalty because they're in similar positions. But if I take a layer over here and match it to a layer over here, then there's going to be a large penalty. The nice thing about this is that you can formulate all of this in a way as an optimal transport program. And moreover, you can prove that the solution to this program induces a pseudo distance in the space of neural network architectures. That is, it satisfies the triangle inequality and all of these properties. So here's an illustration of this distance using a two-dimensional t-SNE embedding just to kind of convince you that this is reasonable. Over here, we have these small networks. Over here, we have these feed-forward-like networks. And over here, we see a lot of branching. And this scatter plot shows that this distance correlates with cross-validation performance. So each x here refers to a pair of networks. And the x-axis shows the distance between these networks. The y-axis shows the difference in the validation error on a real data set. And as you can see, networks that are small according to this distance, that is, the distance is close to 0, they have similar difference, they have similar validation performance. Whereas when the difference increases, then there's more variation. The second contribution in this work is that we developed this method to optimize the acquisition. And the way we do this is that we define a library of modifiers which take in one network and produce a new network. And then we apply an evolutionary algorithm on top of these modifiers to navigate the search space and optimize the acquisition. The resulting procedure is called NESBOT, or Neural Architecture Search with Bayesian Optimization and Optimal Transport. So here's the test error on 7 data sets where we compare NESBOT to 3 different methods. The short story here is that we're doing quite well. And these are some of the optimal architectures that were found using our method. So this is on CIFAR 10. As you can see, there's a lot of skip connections and a lot of softmax layers. This is on indoor location, and this is on the slice localization data set. Our code is up online if you want to learn more, but if you want to test it out. But if you want to learn more, come to poster 166, which is in this room over here. Thanks.
So the next talk is data-driven clustering where we parameterize Lloyd families, and Travis will give a talk.
Thanks. So my name is Travis. I'm going to be talking about data-driven clustering via parameterized Lloyd's families. This is joint work with Nina Balkin and Colin White, all from Carnegie Mellon University. So as you know, a fundamental problem in unsupervised learning is clustering, where the aim is to divide a data set into a group of self-similar clusters. And when we cluster data, usually our goal is to identify some natural clusterings that are actually present in the data. So for example, we could be clustering documents by topic or pictures of animals by species. But in contrast, most of the algorithms we have for clustering fix some cost function, and then they try to drive that cost function to 0, hoping that low-cost clusterings will somehow recover these natural clusters present in the data. But of course, there are many different clustering algorithms, each with different cost functions and different techniques for minimizing those cost functions. And so if you have a specific clustering objective or a specific clustering task that you'd like to solve, an important question to answer is which clustering algorithm will work the best for you. And today we're going to talk a bit about how to automate that decision. So a bit more formally, we're going to think about the following learning model. We imagine that there's some unknown distribution over clustering tasks, and we'd like to find an algorithm that works well for clustering problems sampled from that distribution. And our training data will be a collection of sampling tasks, of clustering tasks sampled from that distribution, annotated with their target clusters. So we have a collection of data sets together with the clusterings that we expected. And we'd like to find an algorithm that produces clusterings that have good agreement with those target clusterings. And of course, a crucial property that the algorithm should also have is that it should work well on new instances drawn from the same distribution. So the basic approach that we take in this paper is to introduce a large parametric family of clustering algorithms that includes popular algorithms as special cases, and then to give efficient procedures for finding the best parameters for this family on a given sample of clustering instances. And finally, to prove generalization guarantees that show that the optimal parameters on a sample will continue to be approximately optimal for the underlying distribution. So the family that we introduced is called alpha-beta Lloyds, and it's a generalization of Lloyd's method or the classic k-means clustering algorithm. And just to remind you, this algorithm maintains k-centers, each defining one cluster, and then performs local search to try to drive the k-means cost of those centers to 0. And the way that local search procedure looks like is you first assign every point to the nearest center, and then you update each center to be the mean of the points assigned to it, and repeat those 2 procedures until the clustering converges. So for example, if this was your clustering data set and the 3 stars were your initial centers, you start by assigning each point to the nearest center, you recompute the centers to be the means of the points assigned to them, recompute the assignments, recompute the centers, and eventually this will converge to reasonable looking clustering. So one of the main things that we generalize about Lloyd's method in our family is we give it a parameterized procedure for choosing the initial centers. And the reason for focusing on this is that the initial centers used by Lloyd's method have a big impact on the clustering quality that you get. So for example, if you accidentally put 2 initial centers in the right cluster, Lloyd's method will never recover from this. But of course, initialization is also a well-studied problem, and there's lots of different proposed procedures. And the best procedure to use for your specific clustering tasks will depend on properties of the clustering instances you're actually facing. So what does alpha-beta Lloyds actually do? So for the initialization phase, we have a parameter alpha, and we're going to use d to the alpha sampling to choose the initial centers. This is a generalization of d-squared sampling from k-means ++. And the way that works is we pick the centers to be from the data set, and the probability that one point x ends up being the ith center is going to be proportional to its distance to the first i-1 centers raised to the power alpha. So for some concrete examples, if we set alpha to be 0, we're just choosing random points as centers. If we pick alpha to be 2, we recover the k-means ++ algorithm. It's slightly biased towards choosing distance centers. And if you choose alpha to be infinity, you're doing farthest first traversal, where you just repeatedly choose the farthest point. And so all 3 of these methods are sort of reasonable initialization procedures for Lloyd's method. We also have a parameter beta that controls how the local search is performed. But for the details, you'll have to see the paper. OK, Cool. So what are the main results in our work? So first, we give an efficient algorithm for tuning the parameters on a sample. So we can find the parameters alpha and beta that give the best possible agreement with the target clustering. And so this shows that it's algorithmically feasible to find these good parameters. Second, we give generalization guarantees by analyzing the intrinsic complexity of alpha beta Lloyds, showing that if you see a relatively large, or relatively small rather, sample of clustering instances, then the optimal parameters on that sample will continue to be approximately optimal on the underlying distribution. So tuning parameters on the sample is a good idea. And finally, we carry out an empirical evaluation of the effect of the parameters alpha and beta on a number of real-world and synthetic data sets. And what we find is that the optimal parameter actually varies quite a lot from data set to data set, which suggests that you can benefit by tuning the parameters on a per problem specific basis. So if you want to talk to us more about this, we're at poster 160 on this floor. Thanks very much.
Hey, the last talk of this session, supervising unsupervised learning. Vikas will give a talk.
Thanks for coming. This is joint work with Adam Kalai at Microsoft. I am a PhD student at MIT. So I will skip this motivation because the previous speaker has already covered. Essentially, the idea is by using a prior repository of labeled data, I could infer on the unlabeled tasks. So these are the main contributions of our work. First of all, we provide a principled unsupervised framework within which you can evaluate the unsupervised settings. This removes the subjectivity inherent in unsupervised learning. We also show how you could transfer knowledge across multiple data sets. These data sets could come from different domains. They may have different dimensionality and all those things. We also show how you could, within our framework, design provably efficient and practically concrete algorithms for a number of problems, including clustering algorithms, choosing the right clustering algorithm, finding the right number of clusters, determining the threshold in the single linkage clustering, removing outliers, and so on. We also remove one of the main problems in clustering. There was a celebrated result by Kleinberg which says that good clustering is not possible in the sense that properties like scale invariance, consistency, and richness cannot be simultaneously satisfied. We show that within our framework you can avoid that and get provably good meta-clustering. Finally, we also show how you could automate deep feature learning across multiple small data sets, and you could do zero-shot learning with new data sets. So this provides preliminary evidence to the fact that you could combine various small data sets from different domains and learn across them. The general approach works like this. We assume there is a meta distribution mu over all the problems in the universe, and the problems in your repository are drawn IID from this distribution. When a new problem comes to you, you just hide the labels and give me the features, and I want to infer the labels for this problem. So the way we model this thing is you have a notion of intrinsic measure which works only on the unlabeled data, so it does not require the labels. And you also have an extrinsic measure which can feature in the labels, and you could evaluate accordingly. This helps us to map from the intrinsic measure to the extrinsic measure, and when a new data set comes, I could compute the intrinsic quality and find the algorithm or the other quantity of interest based on that for the new data. So this is like some evidence. We decided to test our algorithm on number of clusters. So if you fix the k-means algorithm and you run like different k, so it could be on a log scale, it could be on a linear scale, whatever you might feel appropriate. We use the silhouette index as the intrinsic measure for this problem, and the adjusted rand index as the extrinsic measure, and then you learn the mapping. And we conducted these experiments on the OpenML repository, which has like huge number of data sets, and we were able to like consistently beat the direct method, which does not learn across the problems. And besides, the performance improves as the number of training data sets increases. So there is evidence that hopefully with more data sets we can do even better. Also, like we tried with like different algorithms. You could select for the new problem which clustering algorithm to choose, and as the number of data sets increase, we can again say that like there is non-trivial performance by learning across problems. There is a new problem like which is detecting how many outliers should be removed from your new problem. So we saw here that like 1% accuracy, if you remove 1% of the points, you get much better compared to if you do 2%. So this is a completely data-driven principled methodology within which we study this problem. To our knowledge, there is not like a priori any work in this direction. Finally, we introduced this problem of learning binary similarity function. The idea is if I give you 2 points drawn from a problem, whether they belong to the same cluster or not. It can again be analyzed in our framework, and there are two examples of verification here. One is the internal test and the other is the external test. In the internal test, we used some of the training data, so there was an overlap between the test problems and the training problems. So we got like consistently high accuracy. This is not surprising, but on the external test, we did not use any of the data that was used previously, and we still managed to get non-trivial improvements. So this provides evidence that you could combine multiple small data, unite them into big data. How you encode this, please, if you are interested, come by, and I'll be happy to talk more at our poster, which is number 164, and I think the room number has been changed since, so it's probably in the adjacent room. Thank you, and hope to see you there.
So that's the end of this session, and let's thank all our speakers again.